So we will start with some mechanics problems, and towards the end, we'll also look at some problems at class 12th level, including last time you had requested for something in modern physics. So I'm going to do a couple of revision problems in modern physics also. Though actually in my mind, modern physics is one of the easier topics, but anyway, we will do. Okay. So let's start with example 1, which is to do with a mixture of kinematics concepts along with dynamics. So we have a situation like this in this example. We have an inclined plane like this, which is inclined at an angle of 45 degrees with respect to the horizontal. This is a rough inclined plane. So it has a coefficient of friction equal to tan theta equal to unity. Okay. Now what we are doing is we are taking a particle. If we leave it at rest, as you know, it will remain at rest because tan theta is equal to unity. But we are actually projecting this particle with an initial velocity which is horizontal and parallel to the plane. Like this. So this is projected with a horizontal velocity tangential to the surface. So what we see that the particle takes a trajectory which is like this. So this is the situation for the particle at time t equal to 0. So this particle is projected tangentially on the surface. So it's not really projected to move under gravity because it doesn't leave the surface. With a horizontal velocity of magnitude v0. So we have to find, first of all, its acceleration e0 just after projection. And then we have to find its final velocity after a long time. And assuming that the inclined plane is indefinitely long, so this particular length of the inclined plane is extremely long. So L is indefinitely long with that assumption in mind. All right, so just try and work out this question. So again, the key in this question is to understand that at any intermediate instant, okay, not a long time later, but just a little bit later, some intermediate amount of time after you start from here, if you can see that the path of the particle will curve like this. So as it has curved and reached some point in between over here, at that point of time, the relationship between acceleration and velocity, because ultimately we are going to have to make use of that relationship between acceleration and velocity and integrate that and whatever. Okay. So those of you who are here in my first lecture or so, we discussed few things about approach velocity, separation velocity, instantaneous approach velocity, things like that. So this is not exactly that kind of question, but it is kind of based on similar kind of logic. Okay. So just try this out, people. So the first part is very easy. All of you can get the answer to that, I think, without any difficulty. But for the second part, how to understand the velocity after sufficiently long time, you'll also understand how to interpret the question. बहुत long time के बाद velocity पूछ रहा है, that means something must be happening which is very stable after a very long time. And the hint to you is that is to do with the fact that mu is equal to tan theta. Okay, that is why what will happen is that after a long time, it will be in a situation where the motion is quite stable. Whereas initially you can see the direction is constantly changing and something like that. Okay. There's also kind of hint to you in the diagram itself. The dotted curve which is showing you the path, that is also kind of giving you a hint on what is going to happen after a sufficiently long time, provided the inclined plane is sufficiently long also. So this is what I'm suggesting. You start the question by making an FBD at t equal to 0. You'll get your first part's answer. Then you imagine that at some intermediate time, when it's on that curved path, how the free body diagram will be looking like. And therefore, you can start relating free body diagram with this. Okay, Chakshu, your answer is correct for the first part. So I will just start with the first part. People can continue working on it if you have done the first part. So what I'm going to do here to understand the whole question is, system of axis is very important. This is the general kind of path. So what we will do here is we will take this direction as one axis and this direction as another axis. We take a coordinate system such as this is the x-axis and this is the y-axis. So at t equal to 0, we can see that the velocity's direction is along the positive x-axis. Now at t equal to 0, if you also talk about forces, we see that there is mg sine theta acting like this. There will be friction, kinetic friction acting like this. And there are two forces other than this also, which I am coming to. So there is mg sine theta, there is kinetic friction. They will be acting perpendicular to each other. And there will also be the two forces which are along the z-axis. No, not really the z-axis. Yeah, along the z-axis. It's a little difficult to show in this diagram, so we will not show it in this diagram. Instead, what we'll do is we'll also look at if you also look at the inclined plane from the side view. So in this view, we can see that it's like this, okay. And in this view, we would be looking into the YZ plane. So the z-axis would actually be pointing perpendicular but normally outwards, and the y-axis would be pointing like this. So if we are looking at the motion or the dynamics and the forces etc. that are acting on the YZ in the YZ plane, so we will notice that there is also normal reaction acting like this, and mg cos theta acting like this, mg sin theta acting like this. But we can't really see the friction in this diagram for t equal to 0. Just the moment when we've released, this is what it is looking like. So as you can see from here, the acceleration will come as a result of these two vectors. So the acceleration vector will actually be like this, lying in the xy plane, because the z component of forces are cancelling each other. So the net force along the z axis is 0. The acceleration vector like this. So for the first part, that is just at t equal to 0, just after the so what's going to happen there is n is cancelling mg cos theta. So my acceleration acceleration z component becomes 0. magnetic friction is equal to m into x component of acceleration. So this will actually give with proper sign. It will give acceleration x component is minus mu n by mass. So from the first equation, substituting and all this, you get acceleration x component is minus mu g cos theta. Then we'll substitute theta and all this. So this is along the z axis, this is along the x axis, and now finally along the y axis. So mg sin theta is equal to mgy. So your acceleration y component is plus g sin. So your acceleration will initially look like this. It is minus mg cos theta I cap in my reference frame, in my diagram. Somebody else has taken some different system of coordinates, it will have different unit vector notation, but again the magnitude will be the same. And you put theta as 45 degrees and mu as unity here. So you will get the acceleration magnitude at t equal to 0 as g. But the direction is like this. So the acceleration vector will be at 135 degrees with respect to the velocity vector. So that is the interesting thing over here. So, in case you ask something like the radius of curvature of its path initially and all that, that also you will have to take into account, and that is so you can see that E naught by root 2 will be the normal component of acceleration. And minus A naught by root 2 will be the rate of change of speed or the tangential component of acceleration. So various things like this can be asked. Yeah, Ananya, your answers are correct for the second part also. So, the speed is decreasing at the rate of g by root 2 initially, whereas the particle is turning such that it will have a radius of curvature. So this normal component of acceleration can also be interpreted in terms of v naught square by r, where r will be instantaneous radius of curvature. So now if we start comparing this equation to some general intermediate time t, what we'll see that the relationship between the z component of forces always remains. So next what we have to understand that at any instant t equal to t, n minus mg cos theta remains 0. So your z component of acceleration remains. Also, so now if we actually simplify things and just make a diagram looking into the plane. So we are looking into the xy plane. So using the same notation that we had over there, we are looking directly into the inclined plane from the top. So here gravity is going, sort of at an angle for us. Gravity is not along the z-axis. So this is where the motion started from. This is u naught. Now let's say we are looking at some instant when the particle is here. This was t equal to 0. Now the particle is here at time t equal to 0. So it has some instantaneous velocity which will be along the tangent to the path. That instantaneous velocity is like this. So it has some instantaneous velocity. Okay, now let us look at the forces in the xy plane. So as far as the forces are concerned in the xy plane, you will see that mg sine theta will always act along the plane. So this component of force, without a doubt, will have to be like this. Whereas the frictional force, that is the one which keeps adjusting its direction because it is kinetic friction. So the frictional force will always act such that it's causing a tangential deceleration. So this will be your kinetic. So these are the two forces which you can see in this diagram, and of course there's normal reaction and already discussed. So this will be this. So as a result of that, once again you can see that the particle will have a combination of two types of accelerations. Okay, the particle will have, so just to illustrate that point, making a separate diagram of the particle here. This is for t equal to t only, but this is just to show the dynamics, or rather to show the kinematics. So the velocity of the particle is in this direction. At that instant, the particle will have two components of acceleration. One component of acceleration will be a tangential deceleration, and one will be a normal acceleration. It will have a combination of some kind of normal acceleration and some kind of tangential deceleration, which in this case will become minus dv by dt, this kind of thing. Okay, so further, if we now just assume some instantaneous angle like this, suppose as theta. So we can understand in that diagram, theta is instantaneous. Okay. But the magnitude of friction, which is mu m, which is mu mg cos theta, which in this case becomes mg by root 2. This is constant magnitude. So friction direction keeps changing because theta keeps changing. And mg sine theta, on the other hand, is acting like a constant force. Neither direction nor magnitude changes. So that is what we have to look at carefully. So now coming to the dynamical equations from this diagram, and relating these two diagrams, you can see that kinetic friction minus mg sine theta's cos component. Oh, so there's one problem here. I should not use theta because I've already used theta. That will create too much confusion. So what about that? So let's use some different symbol here so that we don't confuse things. So let me just use any other odd symbol, it doesn't matter. So let me take this instantaneous angle as theta or something. Whenever we tend to use the term alpha, we tend to confuse it with some angular variable. So let's not do that. Okay. So yeah, coming back here, this term will also become like this. Okay, so this is our mass into tangential acceleration. So we can see when we substitute here, this will become, oh sorry, this is sine theta. Sorry, many mistakes. This is not sine. This is a constant force. So this remains sine theta. In fact, this is equal to mg by root 2 along the y-axis. This remains the constant. So yeah, so kinetic friction magnitude remains constant, that is mg by root 2. Mg sine theta's magnitude and direction both remain constant. But the component of mg sine theta that is now contributing to tangential acceleration will change with the. So from here we can see that tangential acceleration, which we will write as minus dv by dt is equal to g by root 2 into 1 minus cos beta. So this becomes our first useful equation. This is our equation 1. And you can see that if you integrate equation 1, okay, so suppose at some long time later, t equal to capital T or something, the speed becomes a stable speed. So let's say some final speed. Now I'll explain why it will become stable also. Because that is also important. Without that, you won't understand the logic of why we are doing this. Okay? But assuming that, then we can see that dv is equal to g by root 2 into 1 minus cos beta with a minus sign, of course. So when we integrate this, we'll see that our speed is going from v0 at t equal to 0 to any time actually sufficiently larger than capital T. So we'll just take it as capital T. Is becoming that stable speed v final. So this is telling us that our final speed is minus g by root 2 into capital T minus, as of now, this unsolvable integral, because beta is this one. So this is the modified form of equation 1. So this is what we'll be looking to solve. So I'll just leave you for a moment with the FPD and then we move on. And we'll see again that FPD only and that diagram only will be used to generate a second equation, which will be helping us in finding that integral. So this is where I'm telling you people, those of you who attended my first lecture, that this is related to one of the problems we had done. Even though in that problem we are actually using approach and separation velocity concept. So remember there was one particle chasing another particle that was going off diagonally like that. तो उसमें हमने जैसे components को अलग-अलग interpretation से लेके integrate किया था, and we had removed the variable of that instantaneous angle integrated over time. That similar approach we'll have to take over. And of course, those who have joined later, I have a session video of that and get some interesting problems we solved. So if you just send me a WhatsApp message, I will send you a recording of that session video. You can go through it. Session video as well as the notes. So in fact, if anybody who has missed some part of the previous lecture or anything, you can always, in case you're not getting the session video from our website and all that for whatever reason, you can message me directly on WhatsApp and I will send you whatever is required. Also, I mean, we are having sessions once a week, but you can send me your doubts on WhatsApp, or I will give you my email ID also, in case they are in PDF or something and it's difficult on WhatsApp. You can send them to me, and gradually over time I will clear your doubts. But I can't guarantee that on the same day I might be able to solve and send, because I have lectures and things. But send me your doubts. I will help you out. Within sufficient amount of time, I will clear your doubts. Today, I will pick up some of the questions from the doubts people have posted. But I request that if there are doubts which you want us to solve as teachers, you send them in personal message. It will be easier for us. Because the groups just get overloaded. You know? Then any important information in the groups might get missed. So like whatever physics doubts you can send to me on my personal WhatsApp. Maths doubts to Saurabh sir or Revan sir or whatever. Chemistry doubts like that. Okay, so anyway, hope this is clear. Now, also just a small word about how the motion progresses here as this is moving. So, what we'll also understand before we solve the second equation is why we are so interested in the final velocity after sufficiently long time. Because if we now try to visualize how the motion progresses from this onwards, एक intermediate instant पे तो देख लिया हमने क्या होगा. But if we now just extrapolate कि as time is progressing, where this is exactly going, ऐसा curve तो हो रहा है. But then finally, is it going to curve into a full circle, or is the angular displacement going to be more than 90 degrees? The answer to that is no. what you'll realize that after a sufficiently long time, so between this and this, what is happening? Your velocity is all the time turning, because we saw that your acceleration vector has a normal component in this direction and it has a tangential component in this direction. So at this intermediate time, t equal to t, what is happening? Your v is decreasing with time, okay, and it is turning also. The velocity vector is turning in direction. It is turning like this because of the normal component of acceleration. But imagine some instant, at an instant when v has turned 90 degrees with respect to the initial velocity v1. What happens at that instant? So as this is happening, assuming of course it doesn't stop in between. So that also will justify why it does not stop in between. So the moment you reach this situation here, where the velocity vector has become like this, it has become dead along our y-axis. So that time something very interesting happens for the forces. You see that the forces align. So you see what happens at this moment when you reach this equation here. So this is some, in fact, you see this is why this will become the final velocity. So at this moment, what will happen is that the kinetic friction will be along negative y-axis. And of course, mg sine theta is along positive y-axis. So at the moment when this happens, your force picture looks like this. At that moment, your force picture looks immediately like this. And what will happen as a result of this force picture like this is that because this thing are such, the values are such that kinetic frictions, so since kinetic friction magnitude is mg by root 2 and mg sine theta's magnitude is also mg by root 2. So the moment this happens, your acceleration becomes 0. Okay. So this happens the instant v becomes along the y-axis. Moment this happens, so the acceleration becomes 0. So from this point onwards, it continues with uniform velocity, which is some kind of final velocity along j cap. So that is why it reaches what we can say is that sort of a terminal velocity. It is like a terminal velocity condition. Because the dynamics does not change. There's no reason for friction to change its direction because it will always oppose the velocity. And this way. So it goes indefinitely long period with that constant speed Vf. So that's why this will become the final velocity. And of course, it's not the side of our coordinate frame. So this we are looking at it from the top. So this is our x-axis and this is our y-axis. So we are here, and that's why we understand in the previous example why we are able to integrate it from V0 to V final at some time capital T. So because we are assuming that the first instant when this happens, that it has just about rotated by 90 degrees, this is when the time is equal to capital T, and from there it's continuing like this, it's continuing downwards. So for T greater than capital T, it continues downward at that final. Okay. So hope this concept is clear to all of you. So now it is, you can just understand that it is just a matter of finding a second equation so that we can get rid of this whole thing as a variable, cos beta dt. And that is where that trick that we discussed in that question will become important. कि हमने cos beta को एक तरीके से interpret किया that mg sin theta का जो cos beta component है, that is along the tangential axis. That is along the tangential axis of motion. But another way to interpret cos theta is this, that here this angle is theta. is beta. You can see that if you look at friction's cos beta component, it is basically going to help you find the y component of acceleration. And you know that if you separately integrate the y component of acceleration, what we will get? We will get the rate of change of velocity along the y-axis. So integrate that, we'll get the, so that's the. So what we do now, hit for the second one, friction's cos beta component is along negative y-axis. Okay. So what you do is solve forces y component is equal to m into ay. Okay. So from that you will get the value of ay, and then integrate ay over time from 0 to capital T, and see what that should be. That should give you change in y component of velocity, okay, which you know this is going from 0 to v final, because initially there was no y component of velocity. So use that to generate a second equation. Okay, so use this hint over here in this diagram and this hint. Use this to generate a second equation, and you see that second equation will also be unsolvable because cos beta dt integration will come. But now compare that second equation to the first one, and you can see you will get rid of that cos beta dt integration and that. So this is in that tricky genre of questions of kinematics. Okay. So hope this is clear, people. I think you should not have difficulty now with this, the rest of this question. So I'm just solving that second part below. If you're already on it, just continue working. Just compare my answer later. So you will see that mg sine theta minus friction's cos beta component is the net force along the y-axis. So now just substituting here, let's see. Mg by root 2 into actually the same thing, 1 minus cos theta is equal to m ay, which we can write as m. Okay. So we integrate this. This is our second equation. So in integral form, or this is our second equation. So in integrated form, the equation अभी ऐसा होगा 0 to final t equal to 0. So v final is equal to g by root 2 into capital T minus cos beta dt integrated from 0 to capital. So this is the working formula we're getting in the second. Now you can just compare the first. Comparing between 1 and 2, you can see that right hand. So therefore, equating the left hand sides, v naught minus v final. The right hand side is same with the minus sign is equal to v final. So our final speed becomes v naught by 2. So we will hope this question is clear. Okay, now let's move on to one of the questions which is a sort of combination of let's pick up a question from electrostatics. I want to understand your level of understanding of induced charges and things like that. So, all right, so this is a solid metallic shell of inner radius A and outer radius B. So this is and C is the center. Now what we are doing is, initially we placed one charged particle plus Q1 over here and another charged particle plus Q2 over here at the point P outside, like this, okay. And let's say this point is S. So two particles plus Q1 and plus Q2 are placed at the point S such that the distance CS, center to that point, is known to us. So CS is equal to A by 2, half the inner radius, and Q2, or rather placed at this and the point P, such that the distance CP, center to this one, let us say 3B, 3 times the outer radius, respectively. While the shell is electrically neutral, that means it does not have any charge. So first part, find the net charge induced on inner surface and outer surface, and the potential of let's make this part C, the potential of the metallic shell and the potential at the point C, at the center, how much changes. So these four parts are four subparts are a four part. Now second part, the switch S is closed to ground or earth the shell. We want to find how much charge transfers from earth to the shell. It's a specific question you have to give with algebraic sign, and you have to find the potential at the centers. Okay, so this is the question. So I prefer that at this stage you get the answers just in terms of Q1, Q2, AB. Okay. Though in a numerical question, Q1, Q2 values might be given, AB's values might be given. So you might actually get this numerically, but here let us just solve everything in terms of this. Okay, so get all these in terms of just these 4 parameters. Okay, so this is one single question through which all our concepts of superposition, induced charge, Gauss's law application, everything like that will become clear. Okay. And this is not a very lengthy question. So it should not take a whole lot of time. So you can just give me the answers on chat like this in terms of K Q1 by E, plus K Q2 by V, those kind of things. Just leave out the 4 pi epsilon naught, just write it as P. So just try this out, people. Yeah, Ananya, you have to tell me the charge in terms of Q1 and Q2. But I think based on what you mean in the answer, it should be correct. So I'll just sort of make a rough diagram of how the induced charge will be looking also. So roughly speaking, yes, that's correct. So we have not only this charge particle Q1. The first case, we don't need to worry about this line because this switch is closed. But we also have that charge particle plus Q2, which is lying over here somewhere. So the induced charge that will appear will be like a superposition. So because of this minus, this plus Q1 charge, there will be minus Q1 charge, but that is asymmetrically distributed. It will be distributed like this. The density of charge, the surface density is not uniform. It will be something like this. But this minus Q1 that is distributed is not affected by the plus Q2 because the region of the inner surface is shielded from plus Q2 because of the induced charge on the outer surface. We'll come back to that. Whereas the plus Q2 here will induce some kind of a non-uniform charge on this surface, but also minus Q1 has got induced from the inner surface, so plus Q1 has to come outside. So the outside charge will look very interesting. It will actually have a small amount of negative value here because of the proximity effect of this. But by and large, it will be a positive charge. Something like this. More density of positive charge on this side. Density starts fading. Eventually, it becomes a negative charge. So what will happen is that the inner surface that will have a net charge of minus Q1, but it is asymmetrically distributed. And the outer surface will have a net charge of plus Q1, but that's also highly asymmetrically distributed. In fact, that is distributed asymmetrically to the point that even the sign of charge is similar. So if you also try and visualize the electric field lines, which is not necessary for the question, but the electric field lines will look something like this. Something like this in this image. Then this, something like this. And inside, the electric field lines will all start from the negative charge. Sorry, from the positively charged particle, but then go and terminate normally into this. Like this. So this is what the induced charge is basically doing in terms of distribution of electric field. That's something like critical to understand. So because Q1 and Q2 are not even lying on the common line with the center, okay, so it's really very asymmetrical. But there is no proper axis of symmetry also to the field line diagram, as you can see. Okay. So then you might be wondering how we will calculate potential, and that is where our this thing will come in. Our superposition principle will come in. So now let us talk about potential. So that is your
first ka A part. Now let's talk about the B part, the potential of the conductor. So that is going to be a little bit. So I will actually explain this by superposition. So suppose we had a situation where we had only one of these two events. Let us suppose we had a situation where just plus Q2 was kept over. Then as a result of that, there is, what was this, Q1? So this was Q1 minus 8. Suppose we had this situation where only Q1 was kept inside somewhere over here. So there would be a negative Q1 which is asymmetric on this surface. But there would be a positive Q1 which would be symmetric on the outer surface. So in this case, only Q1 is there. So this would be symmetrical distribution with sigma equal to plus Q1 upon 4 pi b square. And the inner surface would have asymmetric distribution. But a net charge of minus. So as a result of this, what would be the potential of the metal? So the potential of the conductor, so any point inside the conductor would have the same potential as the potential of the surface. And that is very simple. It would just be KQ1 by B. It would be plus KQ1 by B. So you can say that this is the superposition. So this potential that we're getting, it is a superposition of potential due to the particle plus Q1 plus the potential due to the inner surface plus the potential due to the uniform charge Q1 on the outer surface. That together is creating a potential of plus KQ1 by B. Now let us visualize what's happening if we take the other part of the question. Okay, that we have kept a charge particle outside. What that is doing? If that was an independent event, then let's understand what that was. So we just kept a charge particle here plus Q2 now, and let us say it is at a distance B. Later we will substitute that D as 3B. Do that 3 times out. So here अगर अकेले होता, what it would have done? It would have just produced some asymmetric kind of charge on the outer surface. So minus on this side, positive on this side, and no charge on the inner surface. So what would happen as a result of this is that the outer surface would have net charge 0, but asymmetric distribution. Now this asymmetric distribution would be such that the net electric field is 0 at any point in the metal and also any point in the inside the shell, the hollow part, because this would just behave like a solid sphere. So the charge that comes out on the outer surface will be the same as the induced charge that would come on a solid sphere. So it doesn't matter whether it's a solid sphere or a hollow sphere. This induced charge is the same. So the electric field here is also 0, and the electric field here is also 0. Okay. So what happens here? To calculate the potential now, you can see. So therefore, the potential of the metal or of the conductor is equal to the potential of the surface, but it is also equal to the potential at the center. Because right from the surface to the center, any point in between does not have any electric field. तो जितने potential पे ये point exist कर रहा है, उतने potential पे surface exist कर रहा है, उतने potential पे any point here, उतने potential पे any point here, उतने potential पे center. Okay, now why I have chosen the center? Because the center is where we can easily calculate the potential. At the center is potential due to the charge on the outer surface plus potential due to the particle plus. So potential due to the charge on the outer surface is integration of A dq divided by B for the entire outer charge. Plus this is of course K q2 divided by D. So this becomes how much? It becomes A by B, summation of charge on the outer surface, which is 0. This creates a potential of plus KQ2 by D, which in our case becomes plus KQ2 divided by B. Okay. So this is the potential of the conductor because of our second event. Because the potential at any point in the conductor is the same as the potential at the center. So now what we have to do is we have to superpose these two events. So let us say this is event E and this is event B. Now our situation is the superposition of event A and B. So the induced charges that are created on the inner and outer surface because of A and B, they get superimposed. So the contribution that each of the induced charges is giving to the potential of the conductor, that also gets superposed. Okay. So that's how we do this. So just try this out from this point onwards. So just see what will happen when you superimpose this. So Chakshu, you have to check one of your answers out of C and D. You will realize that the potential at the center cannot be equal to the potential of the conductor, because in our situation where A and B are superimposed, there are electric field lines inside. Na? अंदर भी तो electric field lines हैं. So there is some potential difference. So when you go to any point in the in this diagram, when you go from any point in the conductor to the center, you are going across field lines. So there is E dot ds integration. So there is potential difference. So anyway, now let us look at superposition of these two situations. So superposition of A plus B. So I'm not drawing the diagram. We have seen the diagram earlier. Just to save time here. Okay. But what will happen? The potential of the conductor will be potential due to plus Q1 plus V on the inner surface plus V on the outer surface plus the potential due to plus V. Okay. Now we will also understand that V on the inner surface is coming out of the sigma on the inner surface, which is the same as event E. Event A alone is creating sigma because event B के वजह से कोई sigma आया नहीं on the inner surface. You see, in event B, the sigma on the inner surface is 0. 0. So whatever sigma is coming in our final situation on the inner surface is just because of this. Okay. Whereas when you talk about the outer surface, it's actually a superposition of this sigma and this sigma. Okay. So this sigma on the outer surface, this is actually a superposition of sigma outer from event E plus sigma outer from event B. Okay. So further what we can do is
we can write this as V due to Q1 plus V due to sigma on inner surface from event P, because event P was not creating anything, plus V due to sigma on outer, which we are splitting into two. Because remember, potential is scalar, charge distribution is scalar. So we are splitting this into two. Plus potential due to the particle. You can do this. That is the advantage of potential. So now we club all this together. V due to the particle Q1 plus V due to sigma on the inner surface in event P. Club this together. And club these three together. Oh, sorry. 3 on this side and 2 on that side. Plus V sigma outside due to the event A. Plus, now club these two together. V sigma outside due to the event B plus V due to. You see here, this is nothing but V that we are getting for the conductor in event A. And this is nothing but V we are getting for the conductor in event B. Because this is what it was. You can see here. This term, this is V of the conductor in event B. And this term here, nothing but the sum of these two. So this term that we are getting, it is V of the conductor in event E. You have to add this term with this term. So all these three together for giving the conductor a potential of plus KQ1 divided by its outer radius. And these two together were giving a potential of plus KQ2 divided by D. So as you can see, it will become K by B, we can take common. Q1 plus Q2 by 3 we can write, okay? Because in this particular case our D is equal to. So this is becoming the potential of the conductor. This is the part C of question 1. So this is like very intricate logic. It can be a complicated type of JEE advanced paragraph question. Okay. Albeit what I suspect is that if you get something like this, it will be with more symmetry. So your charge particle might be at the center instead of at E by 2 100. It becomes quite lengthy. You should anyway know this because you can get something related to field line diagram and all that. Yeah, Chakshu, your answer seems to be correct now. I'm just taking you through the steps of these. Now you have to repeat these things for the potential at the center. Now in event A, you have to additionally also find out what is the potential at the center in event E. Because that will be different. Whereas here you can see the potential at the center in event B, that is equal to the potential of the conductor. So that we've already got, which is plus KQ2 by B or 3B. So this we already know, but now you have to use a different logic for this and then superimpose these two. So that will give you your last one. Okay, so now let's come to something very interesting. How do you calculate the potential at the center in the first part? Can you calculate it by E.ds integration method? No, because the field inside is not radially symmetric. The field outside is radially symmetric, okay, but the field inside is not radially symmetric. But you can calculate it by summation of KQ by R. Okay, so also another interesting point here. In event A, that is only Q1 inside the shell. At the point we are taken, I think, as S, such that CS was E by 2. That is, okay. The electric field outside that has radial symmetry. Why? Because sigma on the outer surface was uniform. But the electric field inside the shell is asymmetric. Because plus Q1 particle is not at the center. And sigma on the inner surface is asymmetric. So we cannot calculate potential by minus E.ds integration. This method is wrong. We can't do this because the electric field on the inside is asymmetric. But we can calculate potential by using summation of KQ by R or integration of KQ by R. So that is where we can calculate potential only of the center point. So potential at the center will be at potential at the center due to the outer surface charge, sigma on the outer surface, plus potential at the center due to sigma on the inner surface, plus potential at the center due to the particle superposition method. Three types of charges are present. So the outer surface is having uniform sigma, so it will create potential of just plus AQ1 divided by B, because B is the radius of the outer surface. This one will be, it looks like it is problematic, but it is K into integration of dq, but all the charge is equidistant over the inner surface, plus the particle is creating a potential of KQ1 divided by the distance it is at from the center, which is Q. So you can see this has become plus KQ1 by B, plus now this A comes outside and it is integration of total charge on the inner surface. So while while the distribution of charge is asymmetrical, but the total charge we know how much, minus Q1. And this becomes 2 times KQ1 by, taking this 1 by 2 above. So ये कितना हो जाएगा अभी? This will become, the middle term will become minus KQ1 by B. So here, just because you've taken the distance A by 2, you're getting a factor like this, but in general,
So it is so by B. This term is B. If you take A Q1 common, we'll get 1 by B from here, and these two will give minus 1 by A plus 2 by A, so we'll just get 1 by A. But again, that is because we've taken this distance as A by 2. अगर ये कुछ general distance D होता, where D is less than A, then you would have written minus 1 by A plus 1 by D. So this is the potential at the center in event E. Now likewise, the potential at the center in event B, let's see, that was plus AQ2 by B, and D was equal to E. So now the net potential in event A plus event B superimposed. But that same kind of logic we discussed earlier, that it is summation of potential because of all the distributions of charge, and if you plug them together, you will see you will get A into Q1 1 upon B plus 1 upon E plus Q2 by E. This kind of. So this will become a final. So this is the ultimate tricky type of performance. Tricky in terms of logic of superposition. How we logically use superposition in number of different ways. So it's okay if you didn't get this in the first shot and all that, but this is like one question which captures all the concepts of superposition and induced charge. What we call this. Okay, people, so hope all the parts are clear now. Now we come to the final part, that when we ground the sphere, how much charge is drawn from the earth. So in this, now think about the next part like this, that and we have two particles plus Q1 and plus Q2. Q1 is at E by 2 from the center. Q2 is at 3B.
So now you find out how much charge the earth will supply. So again, my advice to you for this part is also think in terms of superposition. If you had a grounded shell with only Q1 inside, and second situation, if you had a grounded shell with only Q2 outside at that case, find out what the induced charges on the surfaces would be in each case. And from that, find out what the net charge of the sphere is for event A and for event B. Then superpose the two and find what is the net charge of the sphere or the shell because of the resultant event of A plus B. And compare that with the initial case when it was not grounded. Initially, it was neutral. So you can find out how much change in charge has occurred, and that is nothing but the charge supplied. Okay. So this is comparatively easy part. It's only the potential part in the last case which was little tricky. Once you understood that, this is a comparatively easier part. Okay, Omkar, I will check your answer. No, Omkar, you have to just verify it once more. There is some wrong factor in. Chakshu, your answer is correct. So, तो just think very logically now. मेरे पास ऐसा asymmetric position पे plus Q1 है और ऐसा एक grounded shell. So grounded shell means that the potential of the conductor has to be zero. that means the potential of the outer surface also has to be 0. So by Gauss's law, you'll understand there's no electric field outside because the potential is 0. That means sigma on the outer surface has to be 0. And sigma on the inner surface is obviously asymmetric, but net charge is minus Q1. So what will the induced charge be looking like in this particular case? It will be an asymmetric but total of minus Q1. In other words, from our earlier event A, if I go to a situation of grounding, the ground will simply remove the positive charge on the outer surface. This will have 0 charge. And this will have minus Q1, but asymmetrically distributed. This kind of stuff. And if you think of the second event now, for that actually the cavity is not even necessary because the behavior would be the same for a solid sphere also as it is for a hollow shell. But anyway, just for the sake of this particular question, we'll understand this. So in this case, if we have kept a grounded shell with a charged particle plus Q2 outside like this, then what happens is that the positive charge is tending to create a positive potential. So this has to draw some negative charge from the earth. So the induced charge, even though even now it is asymmetrical, but it becomes some net negative charge. There might be a bit of positive charge on this side, but predominantly it is a negative charge. The outer surface has some minus Q net charge, which is asymmetrical. And the inner surface has 0 charge. And as always, the electric field in this region is also 0. And the electric field in this region is also 0. Okay. So that is why the potential of the conductor will be equal to the potential of the centers also, which will be 0. Now at the center you can see what is the potential. It is the potential due to the particle outside plus the potential due to the charge on the outer surface. That has to be 0. So this is plus K22 divided by whatever that distance d was, plus K by B integration of dq on the outer surface. Okay. So this gives us the unknown quantity. So potential at the center is plus K into the minus Q charge that it has drawn from the this has to be. So you will see that minus Q charge is actually minus of B by D times. In this case, the minus Q on the outer surface is minus Q2 by 3 because D was equal to 3. Okay. So now superimpose the two events. So इसकी वजह से कितना चार्ज आया था? Because of event 1. Event 1 की वजह से the net charge of the sphere became minus Q1. So delta Q because of event A was minus Q1. And delta Q because of event B is just the charge which has come on the outer surface, which is minus Q2 by 3. So delta Q in event E plus B put together, it is minus of Q1 plus Q2 by 3. One thing you have to be very careful and understand here is that in this case, in event A, potential at the center will not be zero because there are electric field lines inside the cavity. It is potential of the conductor, that thing will be zero. And that means that potential of the surface of the conductor will be zero. Whereas in this case, the potential of the conductor in event B, potential of the conductor is equal to the potential at the center, which is so the method of calculating potential equal to zero and applying the condition for the charge is different for the two cases. Okay, Omkar, you have understood, I hope. And the rest of you also. Okay. Chakshu has got it right, of course. Good. Okay. So one factor was wrong for whatever reason in your calculator. Maybe you made a calculation mistake or a logical, whatever be the case, but make sure you are clear with this now. Now, this kind of a question is very much feasible in your current JEE pattern also. The pehla part humne nikala potential at the center, first part, D part 1's D part, that is like very lengthy and also maybe not in current objective pattern of JEE, it's probably not feasible. But this kind of thing is very much feasible as an MCQ question or an integer type question or something like that. So again, it is superposition principle all the way. Superposition principle. Okay, now another tricky type of question from your class 12 portion that I'll discuss. But now moving away from electrostatics a little bit, moving into transient circuits. Look at an interesting question here. So let's say we have like an easier way of doing this. And we have two capacitors. C1 and C2. Battery of EMF E and resistance R. Now this one is having some initial charge with polarity like this, whereas this one is neutral, one charge. And given that C1 is, let us say, 6 microfarad, C2 is 3 microfarads, and the resistance, let us say 1 kilo ohm, and the EMF of the cell is 12 volts. And the initial charge Q0 is equal to, let us say, .
Just a moment. So let us say it is 8 microcoulomb. That is the initial charge is magnitude on each. Now at t equal to 0, the switch is closed. So first of all, find charges on the capacitors at final steady state. T tending to infinity. Then find the current I naught just after t equal to 0. And then we also want to find the transient current and we also want to plot Q versus T for each capacitor. So try this. So it's the presence of the initial charge which will make it a little bit different from a normal transient analysis question. See, first part's answer you have to give me for the individual capacitors C1 and C2. And you will realize in this case, even though they are in series combination, they will not be the same amount of charge. So this is that very interesting situation where the steady state charge on C1 and C2 will not be equal because they started with some different charges. Initially C1 at Q naught and C2 at 0. If you apply the principles of charge conservation itself, you will understand. In your diagram, take the middle two plates. That is the second plate. Yeah, Bhaskar, your answer is okay. Understood, isn't it? Yes, Bhaskar, your second answer is also correct. For the initial current, what the right answer? Now, at steady state, let me assume that this one has Q1 and this one has Q. So you'll see that conservation of charge will tell you that these two plates together, for example, they form an isolated system. Or even the other two plates, they are connected to each other via a battery. And a battery neither creates nor destroys charge. So the sum of charges should remain constant. So minus Q1 plus Q2 should be equal to plus Q1 or 8 microcoulombs. That is your first part. And then you write your loop equation. So EMF minus Q1 by C1 minus Q2 by C2. So that means first equation is telling you that Q2 minus Q1 is equal to E. Oh, sorry, it's minus. Let's see, these two plates together had a charge of minus Q0. So this plate was having minus Q1. So minus Q1 plus Q2. Minus Q1 plus Q2 is equal to minus Q. So Q2 minus Q1 is 8 microcoulomb. Q1 minus Q2 is 8. And the second equation will tell me that Q1 by C1, that was 6 microfarad plus Q2 by C2, which I think was 3 microfarads. Was it 6 and 3 or 3 and 6? 6 and 3 is equal to the EMF, which was 12 volts. So you can say that Q1 plus Q2 is equal to 72 microfarads. So Q1 plus these are my equation 1 and 2. For example, if we just subtract these two, we get Q2 as 72 minus 8 by 3. That should be 22 microcoulombs. And you get Q1 as 30 microcoulombs. Let's just check. Okay, 64. Something is going wrong. Q2 is equal to
What are the answers you people have got? 88 by 3 and 64 by 3. So when you substitute this over here, this will become 64 by 3 plus 8. That is 24 plus 88 by 3. We get these. So that's okay. Okay. Now the thing is, also initially you can see at t equal to 0, if you draw a circuit loop equation, it's like this. Then 0 charge. You just write a KVL loop equation. So this current is I naught. You'll see you'll get E minus Q naught by C1 minus I naught R. There's no potential drop. So from this you will get your I naught as 32 by 3 milliamperes or 10.67 milliamperes. As a couple of you got this correct. This is the initial. So that's also not very tricky. Now let's come to the transient analysis part. So transient analysis के लिए what we do is we look at the same circuit diagram, but at some intermediate time now. So at some time t equal to t, if you look at it, the charge on this would have increased to Q1. The charge on this would have increased to Q2, where you will understand that the battery has supplied Q amount of charge to the current I. Suppose the battery has supplied Q amount of charge, so my Q1 is actually equal to Q0 plus a transient Q, and my Q2 is just equal to that transient, and my instantaneous current is the rate of that charging. So you get this kind of thing. So you can see that your loop equation E minus Q1 by C1 minus Q2 by C2 minus IR is 0. Now when you substitute these over here, next step you will get is that E minus Q0 plus Q by C1 minus Q by C2 minus R dQ by dt is equal to 0. So you get kind of a standard equation. If you just separate out this part. This is a constant minus Q into 1 by C1 plus 1 by C2 minus R dQ by dt is equal to 0. So just think of this entire section as a new constant E prime minus Q upon some equivalent capacitance, where that equivalent capacitance is nothing but the series combination of this. So series combination of 6 and 3 will give you 2 microfarads. That is that value here minus R dQ by dt is equal to 0. So you'll get your Q as a standard. Q will be some steady state value of Q.
1 minus e raised power minus t by tau, where that steady state value of charge will be equal to e prime into c equivalent. So that over here will become e minus q naught by c1 multiplied by c equivalent. So it will be 12 minus 8 by 6 microcoulomb and microfarad, so that's fine. It's still in volts, multiplied by 2 microfarads. So this will give us how much? 32 by 3 into 2. So 64 by 3 microcoulomb. Which, by the way, you remember was at steady state our Q1 will actually be Q naught plus the steady state charge. That will come out to be 88 by 3. Whereas our Q2 will be just the value of the steady state charge. We got earlier as 64 by 3. That's all fine. But more importantly, यहाँ पे tau का value क्या हो जाएगा? Tau का value हो जाएगा R into C equivalent. So that is 1 kilo ohm multiplied by 2 microfarad or 2 milliseconds. This is the value of tau. This is the value of. So now, as far as your current is concerned, so your current is dq by dt. So just apply the differentiation thing here. The current should be that exponentially decaying term. It should become some I naught into e raised power minus t by tau. And this will also verify the value of I naught we had got in the first or in the second part. So I naught here will just be steady state charge divided by time constant, which you saw was 64 by 3 microcoulomb divided by 2 milliseconds. So this is nothing but 32 by 3 milliamperes. Micro divided by milli. This also checks out to what we have got earlier. That's done. And finally, the graphs will look like this. In fact, let's do all three graphs: the current versus time, Q1 versus time, and Q2 versus time. So the current is decaying with time. An exponential decay like this from I naught. The charge on the first capacitor will increase exponentially, but it will go like this. From the value Q naught to the steady state value Q1. In fact, the charge on the first capacitor as a function of time will be like this: Q naught plus steady state charge into 1 minus e raised power minus e by tau, where Q1 is actually equal to Q naught plus Qs. That's it. write it like this also. Whichever way you write it, when you substitute the numerical value is the same. That's how this charge will be. Whereas the second one's charge, that is starting from 0 and going to the steady state value. So your Q2 as a function of time become capital Q2 into 1 minus e raised power minus t by tau, where your capital Q2 is of course the steady state charge. So this is the complete description of this. So the differential equation solving part was not different. We didn't have to use any Thevenin equivalent and all that. We just use the standard differential equation which we see for exponentially decaying quantities amount. Okay, people, now unfortunately there's been some confusion with the timetable. Normally our lecture is supposed to be on Wednesday and suddenly it was scheduled today. I have another appointment actually which I just came to know at 1:30. So we'll have to cut short here because I need to get ready for the second one. So we will continue from this point in the next lecture, and I was not able to come to any of your doubt questions today. I kept it for the end anyway. But the suggestion is that, if you can physics doubts, you can also send to me personally on WhatsApp, and I will try to give you some hints on WhatsApp and all that. And then, through the week, I will select some good questions out of the doubts that you are sending. And the ones which I'm not able to send immediately, the solution or whatever, I'll pick out few of the questions for every one of these sessions, and few of the questions I have some things in mind because I want to revise certain key parts for your JEE Advanced through these questions. So, today you will realize that we've covered a lot of ground. We have done a thorough revision of induced charge and grounding and those kind of things. We're literally using that question as a reference. Any type of problem involving that situation, grounding and induced charge and potential of a conductor and all that, you'll be able to do just using that as a reference, and that the logic of the superposition method. Okay. Similarly, the kinematics question, it was a trick-based question, but a lot of things are covered through that: friction, limiting friction, tangential acceleration, normal acceleration, those kind of things. So that is the idea, that in each session we pick up some questions through which we are doing some revision of the advanced theory concepts, keeping your JEE Advanced exam in mind. Okay, so we'll have to cut short today, and that's it for today. People, hope you've understood all the things in the lecture so far. Okay. As always, I will be sending you the PDF file of the whiteboard as well as the video of the lecture notes, so you can use that as a reference. Okay, so that's it. Thank you, people. All the best.